Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. In this project, I will create a panoramic image with OpenCV and Python. So the problem is, given two separate images, I have to stitch them together to create a panoramic scene. And also note that both the images need to share some common regions. And also the solution need to work even if the images are of different scale, they have different angles or perspective or different capturing devices. Let's start. Now, what is image stitching? A technique of combining several overlapping images from the similar viewpoint into a bigger one without trashing of information is known as image stitching. The most universally used methods for this is Harris corner detection and shift, that is a scale invariant feature transform. And then what is image matching? The concept of feature matching, or generally image matching, is a part of many computer vision algorithms such as image registration, camera calibration, and object recognition. It is a task of establishing correspondence between two images of the same scene or same object. A common approach to image matching consists of detecting a set of interest points, each associated with image descriptors from the individual image data. Once the feature and their descriptors have been extracted from two or more images, the next step is to establish some preliminary feature matches between the images. And then the very important concept of feature descriptor. A feature descriptor is an algorithm which takes an image and outputs locations, that is pixel coordinates of significant areas in your image. An example of this is a corner detector, which outputs the location of corners in your image but does not tell you any other information about the features detected. The locations might also include a number describing the size or scale of the feature. This is because things that look like corners when zoomed in may not look like corners when zoomed out, and so specifying the scale information, the scale data, is very important. So instead of just using an XY pair of location in image space, you might have a triple, that is X, Y, and scale as location in a scaling in a feature space. So feature descriptors encode interesting information into a series of numbers and act as a sort of numerical fingerprint that can be used to differentiate one feature from another. Ideally, this information would be invariant under image transformation, so we can find the feature again if the image is transformed in some way. After detecting interest points, we go on to compute a descriptor for every one of them, and descriptors can be categorized into two classes: local descriptors and global descriptors. So local descriptor is a compact representation of a point's local neighborhood. Local descriptors try to resemble shape and appearance only in a local neighborhood around the point, and thus are very suitable for representing it in terms of matching. And then the second one is global descriptor. A global descriptor describes a whole image. They are generally not very robust, as a change in part of the image may cause it to fail, as it will affect the resulting descriptor. Now, these are the main feature descriptor used in the world of computer vision: shift, sharp, brisk, and brief. And each of them are founded on very robust mathematical foundation. And definitely in this video, I'm not going into the details of each one of them, but at least a top level understanding of them is necessary. So methods like shift, scale invariant feature transform, or SARF, that is speeded up robust feature, try to address the limitations of corner detection algorithms. Usually, corner detector algorithms use a fixed size kernel to detect regions of interest or corners in an image. And it is easy to understand that when we scale an image, that is enlarge it or reduce it, this kernel might become too small or too big, because the kernel size remains fixed even though the image is scaled. So to address this limitation, methods like shift uses difference of Gaussian, DOG. The idea is to apply DOG on differently scaled version of the same image. It also uses the neighboring pixel information to find and refine key points and corresponding descriptors. So when you have two identical images, except one is scaled differently than the other, Shift maximizes the difference of Gaussian or DOG in scale and in space to find same key points independently in each image. And DOG is basically the difference of the Gaussian blurring of an image with different standard deviation. Every octave or scale of the image is blurred with Gaussian with standard deviation of different scaling factors. The differences between adjacent Gaussian blurred images are calculated as DOG. The process is repeated for each octave of scaled image. And here is a little comparison between Shift and Harris corner detection algorithm. The Harris detector is rotation invariant, which means that the detector can still distinguish the corners even if the image is rotated. However, the Harris detector cannot perform well if the image is scaled differently. And that means that Harris algorithm is not scale invariant. And that's where Shift comes. Due to the characteristics of Shift, the key point descriptors under Shift are constructed to extract features by finding the precise positioning and main direction of feature points in different scale spaces. Hence, it is scale invariant, and of course, Shift is rotation invariant as well, making Shift a great feature detector algorithm. And now finally, here is the overall workflow of this project. I have two separate images of Singapore, the left one and the right one. So one of these images is a query image, another one is train image. So, and the problem here that I have to match the query image with the train image to create a whole wide panoramic image, and they should be completely stitched together and mapping their feature points. That is, I cannot just add one image to the right of another and then have the panorama. No, that's not how it works. It has to match the features. That is, this particular building, probably here is a corner, or here is another feature, here is a room, and that needs to match with this building image here. And again, one of the requirement is those two images should have some common areas, and these two images, as you can obviously see, that there are quite a bit of common areas here and here in this area. And so this is a problem, and the overall flow of the work is this, that is, this project consists of 4 steps. Step number 1 is detect key points under Harris or Shift or Surf from the 2 input images. Then step 2 is match the descriptors between the 2 images. So when I apply Shift or Surf or Harris, they will return me a set of descriptors, which is a set of vectors, numerical vectors, and then I have to match them. Then step number 3 is use the RANSAC algorithm, that is random sample consensus, to estimate the homography matrix using our matched feature vectors. So we will come to what exactly RANSAC does and why we need a homography matrix in a while during the project. But for now, this is our step 3. And finally, apply a warping transformation using the homography matrix obtained from the previous step and get the final panoramic images. So that's the plan. And let's start with the code now. And I am in my VS Code now in the root project directory. This is my notebook, and in the same directory of the notebook, I also have these query image and train image. Let's quickly have a look at this. So this is my train image, and the other one is the query image. So let's start with the notebook. All right, so first, the standard imports. I'm importing CV2, NumPy, Matplotlib, and image.io. And then let me define some variable as a very first step. Feature extraction algo. This is the algo that I will be using. So Shift. So this is my starting algorithm, and I'm defining it as a separate variable because these variable I'll be using throughout the project, and while checking which algorithm works best, we can just change it here, and the whole project will run on a different algorithm. And also feature to match should be under brute force. Feature to, it's a feature matching algorithm, brute force. I'll talk about that a little bit in a while. That is BF. And next is I will actually start reading the two images that I have in this folder. So make sure that the train image is the image that will need to be transformed. So train photo equal to cv2 dot, it's in the same root directory, so I'm just passing, okay, train.jpg. And then I have to convert BGR to RGB because OpenCV defines the color channels in the order of BGR, blue, green, red, and matplotlib recognizes them in red, green, blue. So I have to convert the channels accordingly. It's a standard process. We have to do this kind of things in most computer vision project. Train photo equal to 2.cvt color, and the first argument is the input image, train photo, and the second argument is cv2 dot color bgr to RGB. Okay, looks like that's what I want. Yes, BGR to RGB. Yes. And also I need the images to be converted to grayscale before passing them to shift. So train photo cv2 dot cv2 color cv color, input is train photo, and cv2 dot color RGB to gray. All right. And I have to do the same for the query image. So let's query image cv2.imread. Query.jpg. Then converting from BGR to RGB, query image equal to cv2.cvt color. First input is the input image, and then cv2 dot color bgr to RGB. And finally, converting to grayscale, query image underscore cv2.cvt color, query image cv2 dot color RGB to gray, RGB to gray. That should do. Now view or plot the images. AX1, AX2. SUB. Subplots. Actually, it will be subplots because I have to plot multiple of them.
And number of rows will be 1 in ROWS equal to 1. Number of columns will be 2 because I'm plotting 2 images side by side. Constraint layout, TRAINE. I'm setting it to false, and fixed size, let's keep it at 6, fixed size equal to, let's keep it 16 by 9. And then im show ax1 dot im, oh sorry, ax1 im show, that would take the query photo, query image. And actually, to be consistent, I want to rename this query image thing to query photo because I have named the train photo accordingly. So let's do that. Replace all of them with query photo. Replace all, yes. And similarly, query image gray to photo. Okay. Sorry, that would be GRAY. Photo. All right. And ax1.im show query photo, and that would take the second parameter cmap cmmfp equal to cmap gray. And now ax1 dot set xlrdel. That is my query photo. So let's just put it accordingly. Photo. And font size equal to 14. And I got to do the same for the train image as well. And so for the train image, I can just copy this whole thing first and just change the query photo to train photo, TRAIN, and just mentioned it here. The train photo is the photo to transform. And I think the other things just will remain the same. ax1 set x label. Okay, let's just run it now. Oops, sorry, I do not need these line. It's got just duplicated. And this one also will be ax2 because now that's a different axis. All right, now let's run it. So run all. And I got two of my images, that is a query photo and the train photo, plotted side by side. And now I'm ready to invoke a function to get my descriptors on the image. So I'm going to use the very well-known OpenCV function called detect and compute, and it has to be invoked like this. So first you create an object called shift, which is equal to cv dot, actually it will be cv2 dot shift create, and then on this object shift you invoke this function detect and compute, and that will return me two things, keypoints and descriptors. And what exactly are they? So in this code, the keypoints will be a list of keypoints, and descriptors is a numpy array of shape number of keypoints into 1 to 8. Now, before I go ahead and write the code for it, just one fundamental thing to understand, which is very important for any computer vision project, that why I need these two things, that is keypoints and descriptors, to be returned from detect and compute. Why not just keypoints is enough? So to understand that, you have to first know that after extracting the key points, you only obtain information about their position and sometimes their coverage area, usually approximated by a circle or ellipse in the image. While the information about key point position might sometimes be useful, it does not say much about the key points themselves. that is, you can imagine about the metadata of the key points themselves. So depending on the algorithm used to extract key points like shift, Harris corner, or MSER, you will know some general characteristics of the extracted key points. For example, they are centered around blobs, edges, prominent corners, but you will not know how different or similar one key point is to the other. And that's very important to know. Here's why. First, I take a simple example where only the position and key point area will not help us. So imagine you have an image A of a bear on a white background and another image B, exact copy of A, but translated for a few pixels. The extracted key points will be the same on the same part of the bear. Those two images should be recognized as same or similar. But if the only information we have is their position and that changed because of the translation, like scaling or some other kind of transformation, you cannot compare the images just with the key points information. So if you have an image A, let's say of a duck this time, and another image B, exactly the same duck as in the image A, except twice the size, the extracted key points will be the same parts of the duck. Those are also same or similar images. So basically image B is exactly similar to image A, only twice the size. So a human can very well understand the difference and can decide that they are the same image, although the sizes will be different. So for a computer, all the key points from image B will be twice the size of those from image A. So just the key points, that is just this vector that is returned from the detect and compute, will be confused. They cannot make a decision that they are the same images because it has been translated or scaled in this case. And here come descriptors. They are the way to compare the key points. They summarize in vector format of constant length some characteristics about the key points. For example, it could be their intensity in the direction of their most pronounced orientation. It's assigning a numerical description to the area of the image the key points refer to. And so now with both the key points vector and the descriptors vector, a computer can make a decision that those two images A and B are the same, even though their scales is different. So that's basically why we need key points and descriptors, that is both these two parameters to be returned from my shift dot detect and compute. Now some important things for descriptors are that they should be independent of key point position. Now, if the same key point is extracted at different position because of translation, the descriptor should be the same. And also they should be robust against image transformation. Some examples are changes of contrast. For example, images of the same place during a sunny and cloudy day, and also changes of perspective. Images of a building from center right and center left, we would still like to recognize it as the same building. And with descriptors and key points, a computer can do that. Of course, no descriptor is completely robust against all kind of transformations or against any single transformation which is very, very strong. For example, a very big change in perspective. But that's just an expected limitations of computer vision algorithm as of this moment. And that is nothing to worry about for most of our regular projects. And different descriptors are designed to be robust against different transformation, which is sometimes opposed to the speed it takes to calculate them. And final point about descriptor, which is almost obvious by now, is that they should be scale independent. The descriptor should take into account the scale in its calculation. An example: if the prominent part of one key point is a vertical line of 10 pixel inside a circular area of radius 8 pixel, and the prominent part of another vertical line of 5 pixel inside a circular area with a radius of 4 pixel, these key points should be assigned similar descriptors. And at this point, just note that these are the four main feature descriptors algorithms we have, that is shift, sharp, brisk, and brief. And now I'm going to write a code to conditionally take any of these four in my project. So this method will conditionally select one of the descriptors. So the method name is select, SCRIPTOR and it takes the input image and a method. The default of it's none. And a quick test of asserting. Assert, if the method is not provided, then the user should be given a prompt. Method is not none. Otherwise, please define this IP to your descriptor method. Accepted values are let's do this. SIFT, SURF, ORB, and the last one is brisk. Okay. If method equal to sign of p, then my descriptor will be RIPTOR. My descriptor will be cv2.shift create SIFT. This one. Similarly, just copy this code. And change it to surf, SURF. This will be surf create SURF. And if this is brisk, this will be brisk create, BRISK. And the last one is ORB, then it will be ORB create. All right. And finally, it will return a tuple of key points and features like we discussed for so long with the presentation. Key point, POINTS, and the descriptors or features. So DSCRIP descriptor dot, I have to make use of the detect and compute function of CV2. And detect and compute. And it takes the input image and none. Sorry, this is a spelling mistake, image. All right. And then I'm just returning these key points. Return key points and features. Okay, that should run well. Yeah, and now in the next, I'm going to invoke these function. So I'm going to apply the select descriptor method on both the train image and the query image. Let's write that key points, train image, and feature train image equal to select descriptor method. And the first input would be the input photo, train photo grayscale version, and method. Remember, this method is one of these algorithm that is sorry, one of these algorithms, shift, surf, brisk, and ORB. And at the very top of the notebook, we have set a variable, feature extraction algo, and that we have set it to shift. So here we can change it here. So let's come back and pause the method to be equal to that variable. And I'm going to do the same for my query image. Feature query, and as well as this one, QRY. All right, let's run it. Yeah, it ran. Let's just print it. and see what they print. So the key points, I guess that if you print the key points, it may not be completely understandable. I mean the printed version of key points, but I will come back to that in a second. So let's just first print it to see its form. All right, this is my key points. Can you make any sense of it? We cannot, but I will come back to it later. Let's also print the descriptor, and the descriptor should be just a numpy array. Okay, feature. What is that feature? Yeah, this is the descriptor of the key points. So I'm just printing it now. Yeah, this is just a two-dimensional numpy array. And okay, so now let's quickly revisit what the key points are. Now, to come back to the point of understanding the key point, when I printed these key point returned from the select and descriptor method, this is what we got. And this is actually coming from this function, detect and compute of OpenCV. So let's quickly see the structure of these. So the syntax of OpenCV key point is something like this. It returns x, which is a position of the key point with respect to the x-axis. Y is a position of the key point with respect to the y-axis. Size is the diameter of the key point. Angle is its orientation of the key point. Response, also known as the strength of the key point, it is the key point detector response on the key point. Octave is a pyramid octave in which the key point has been detected, and class ID is the object ID. And apart from octave and class ID parameters, which have integer values, other arguments have float values. And you can read further on these in the OpenCV's documentation here in this link that you see on my screen right now. So they also mention the same thing. Public attributes, we have class ID, octave, etc. And there's some detailed explanation as well. The class data structure for salient point detectors. A class instance stores key point. That is a point feature found by one of the many available key point detectors. The key point is characterized by the 2D position scale proportional to the diameter of the neighborhood that needs to be taken into account, orientation, and some other parameters. The key point neighborhood is then analyzed by another algorithm that builds a descriptor, usually represented as a feature vector. The key points representing the same object in different images can then be matched using KD tree or another method. All right, now let's move ahead. Actually, let's just quickly understand this key point constructor. That is what underlies these values a little bit, so that it can be completely clear. So I'm going to write a little bit of code, only a couple of lines to get inside this key point. Let's clear this output first. Okay. Yeah. For key point. So I'm looping through each elements of my key points that has been returned from this function. So the select descriptor and method has returned me key points query image. I'm going to loop through that. Yeah. And just want to mention again that the syntax you already discussed. The syntax of OpenCV key point is like this, that x and y is the position of the key point with respect to x-axis and y-axis. Then I have size, angle, which is the orientation of the key point, the angle. Size is the diameter of the key point, because key point will kind of give me circular or elliptical space around the key point. And then I have response and octave and class ID. So let's just print them, then it will be clear. Key point in key point query image. Now the first one is xy, which is a tuple returned from keypoint.pt. Keypoint.pt. Size is keypoint.size. Then I have orientation equal to dot angle, and then response equal to keypoint.response, RESPON, then octave equal to dot RCV, and the last one is class ID equal to one dot class ID. I can actually print them here. So let's print them inside the loop. Let's print X and Y, but I think the Jupyter Notebook cannot show all the values if I print them inside the loop because there are so many key point that has been found. So let's try anyway. Let's run this cell. 1 second. CV2.keypoint object has no attribute called yeah, the spelling mistake. Octave. Yep. All right, yeah. Like I expected, output exceeds the size limit. Open the full output below in a text editor. So you can see that they're trying to print. So these are my X and Y values. First one is X value and the second one is Y value. This is the X and Y coordinates of the key points. And I can try to open it in a text editor and then it will show me all these values. The list is really, really long. So yeah, that's how it is. But let's just quickly print all of them outside the loop so I can see what they are. Yeah. So much information was actually extracted by that detect function. What is that function? That detect and compute function. Okay. Yep. Print XY, then print size, print orientation, print angle. No, sorry, response, RESPONSE. Class ID. So this is going to print a single value only. That is the last value. Let's put a string around them. Size. Sorry. Response. Oops, sorry. Response. And this is octave. Okay, now it should print all of them. Let's run this cell. Yeah, awesome. So the first one, I got X and Y. Size is this number. Orientation is these. Response, octave, and class ID. And note, like the documentation has clearly mentioned, octave and class ID is of type int, and the rest ones are all type float. All right, so that was my key point. And now I also want to understand the building blocks of the descriptors or the features. That is the first parameter returned was the key points from this function, and the second was the features. And if we printed the features here, I got a vector. Yes, this vector is of shape 128. Let's understand this vector as well. So earlier I mentioned that this descriptor is returned from this function is a NumPy array of shape number of key points by 128. So let's check that this is really so. So let's first print the shape of this feature vector, which is feature query image. I'm just printing the shape. And that should give me, yes. So that gave me, it's a vector of size 4922 by 128. Now 128 is returned, that we already know, it's a constant that for shift algorithm, it will be 128. And I will come to this point that why it is exactly this 128, that is from where exactly this number is coming. But 4922 is number of key points. Now we can check that as well. If you print yeah, I don't need the print statement. Print the len of my key point query image, because we are doing these both for the query image, and that would give me 4922. So this is the number of key points that we have, and that's why this feature vector is 4922 by 128. Now let's come to understand that from where the value of 120 is coming in shift descriptor. So first, the workflow of shift is like this, that running shift on an image will return many key points, each of which has an associated descriptor or vector describing the region around that point. And when a key point descriptor is created, a 16 by 16 neighborhood around the key point is taken. It is divided into 16 sub-blocks of 4 by 4 size. For each sub-block, 8 bin orientation histogram is created. So a total of 128 bin, that is 4 into 4 into 8 values are available. It is represented as a vector to form the key point descriptor, and that's how I get the 128 number. Now I'm just going to take a quick look at the original paper here by the famous, this was a landmark paper published in 2004 by David G. Lowe. This is where these shift scale invariant feature detection first was proposed, and it's really a landmark path changing paper in the history of computer vision. So if you look at the most popular image or representation of shift from this paper, this is that image. So what it does is that a key point descriptor is created by first computing the gradient magnitude and orientation at each image sample point in a region around the key point location, as shown on the left. These are weighted by a Gaussian window indicated by the overlaid circle. These samples are then accumulated into orientation histograms summarizing the contents of 4 by 4 subregions on the right side of this image. So this is that 4 by 4 subregion, with the length of each arrow corresponding to the sum of the gradient magnitudes near that direction within the region. So this figure shows a 2 by 2 descriptor array computed from an 8 by 8 set of samples. So again, basically in shift, the 128 dimensional feature vector is made up of 4 by 4 samples per window in 8 directions per sample, giving us 4 into 4 into 4, that is 128 dimension vector. And that's how we get this number of 128 in shift. All right, so now that we have the key points and the features of the query image and train images for both, let's draw the key points on these two images. So I'm going to use the plot function again, fig, and it will be 2 images for train and query with the key points on top of them. So I need x1 and x2 as tuple, and then plt dot subplots. Number of rows should be 1. Number of columns should be 2, because there are 2 images. Fig size. Let's keep it 20, 8. And also I'm setting the constraint, say strained layout to false. Now, for this constraint layout, this particular thing in our previous plot as well. Here, I set it to false. Where is that? Here. So, what exactly is this constraint layout? So, it's still very new, and I think it's still experimental in Matplotlib. So, basically, constraint layout attempts to resize subplots in a figure so that there are no overlaps between axis objects and labels on the axis. So constraint layout automatically adjusts subplots and decorations like legends and color bars so that they fit in the figure window while still preserving as best as they can the logical layout requested by the user. So it's very useful when you have many subplots, but in this case I'm setting it to false, the reason being that it's still experimental, and also when you want your result to be absolutely reproducible, then it's better to keep it at false for now. All right, so that's pretty much the reason. Now let's move ahead. Constraint layout false, and then my ax1 dot imshow cv2 dot. So here I'll be using a particular function of OpenCV called draw keypoints, and that will take my input image, train photo gray, then keypoints train image. Then the third one is actually for the output image. I'm setting it to none for now, and color equal to 0, 255, 0. And then ax1 dot set x label let's give a and font size equal to 14. Okay, and similarly I'm going to do for the query image x2 aim show cv2 draw keypoints trend query 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 photo keypoints trend photo none, and the color remains at this. Okay. Oh, this will be x1. Set x label, and let's name it b, font size 14. All right, and now blt dot save figure. I'm going to save figure, and then let's output. I'm just outputting this to a different folder in my root directory of the project. Feature extraction algo plus let's feature RNG, and I'm saving it as a .jpeg format. Okay, and the last one is bbox inches and tight. So setting this bbox inches to tight is this is a concept about the tight layout in Matplotlib. So tight layout automatically adjusts subplot params so that the subplots fits in to the figure area. This is an experimental feature again and may not work for some cases. It only checks the extents of tick labels, axis labels, and titles as well. So basically, if the axis labels in your plot gets cut off in the saved image, then you set bbox inches to tight. And quickly look at the documentation of save figure. So what they say for bbox inches, it's a bbox actually is a bounding box in inches, and only the given portion of the figure is saved if tight. Try to figure out the tight bbox of the figure. All right, let's go back to our code. All right, so I've set it to bbox tight, and now, okay, so I have further few parameters to set. DPI equal to 300, and let's set optimize to true. Optimize equal to 300, and format, because I set it to .jpeg. Now here also I need .jpeg. All right, and now finally just plt.show. Let's run this. File not found. Okay, let's resolve this first. Oh, I think I got this file not found because I have mentioned the plt.save figure to be saved in an output directory, but there is no output directory in my root of the project. So let's create that one. Output. And now if I run it, it should run. Yeah. All right. So this is my two plots of the images, and all these green circles that you see, they are the key points. Let's quickly now understand how these draw key points function actually works. And yeah. So in order to be able to draw the detected key points on a given image, we make use of a function called draw key points function in OpenCV. The draw key point function takes takes as input these parameter input image, key points, output image, color, and flag. So here the input image is an image from which the key points are derived using shift or surf algorithm. Key points are the key points. We already saw that. Output image is the image on which key points are drawn in circles. Color represent the color of the key points drawn in circle. In this case, I drew all of them in green. And flag represents the drawing features. There are quite a few acceptable values for flags. Let's quickly put in here. So the possible values of flags are these: that cv dot and this is actually cv2. Cv2 dot draw matches flags default, draw reach key points, draw over out img, not draw single points. Of course, you should really go to their documentation to check out the meaning. Now, overall, these the key points drawn using draw key point function are special because even if we rotate the image or shrink the image or expand the images or translate the images or distort the images, the key points remains the same in the modified image when compared to the original image. The key points are scale invariant. I mean, that's how the key point here are scale invariant and are circular. The draw key point function returns an image with key points drawn on the image, which is what we did here. All right, now let's move ahead. All right, now that we have all the key points, now it's time to match those key points, and I will be using brute force matcher. So brute force matcher or BF matcher matches a descriptor of a feature from one image with all other features of another image and returns a match based on some distance calculation. So in other words, given two sets of features from image 1 and image 2, each feature from set 1 is compared against all features from set 2. It is slow since it checks match with all the features. Let's first create a basic code to return me a brute force object, and then I will be talking more about how it works. So div create matching object, create. That will take a method and cross CHECK. We'll see in a second that what these methods and cross-check is all about in brute force. So for BF matcher in OpenCV, first we have to create the BF matcher object from cv2.bf matcher. So let's create that. If method is equal shift SIFT or method equal to serve. Then let's do the BF equal to cv2 dot, the function is BF matcher, and it takes two parameter. One is cv2 dot norm L2 norm underscore L2, this one. Yeah, I will explain in a second that the difference between norm L2 and norm Hamming for the first parameter of brute force. And the second one is cross check. Let's give equal to 0 cross check. And L if method equal to ORB or method equal to brisk, ISK. Then my BF should be ORB and brisk are like binary methods of image detection. So in this case, my first parameter need to be binary distance, which is norm Hamming. BF equal to cv2 dot BF BF matcher and cv2 dot norm Hamming and ORM Hamming. Yep. And cross check remains cross check. All right, and finally return the BF. And now about the parameters of BF matcher function. So I have got two parameters here. One is the first one, norm type, and the second one is cross check. So for norm type, there are two options: norm underscore L2 and norm underscore Hamming. The first one is for Euclidean distance or L2 distance, and the second one is for Hamming distance. And the norm underscore L2 is by default, that's a value, and it is good for detection method like shift, surf, etc. And for binary string based descriptors like ORB, which stands for oriented fast and rotated brief, then brief method, that is binary robust independent elementary features, and also for brisk, the Hamming distance should be used, which is cv2 dot norm underscore Hamming. And the second parameter is Boolean variable, this cross check, which is false by default. It indicates whether the two features have to match each other to be considered valid. If it is true, then matcher returns only those matches with value ij such that ith descriptor in set A has jth descriptor in set B as a best match, and vice versa. That is, the two features in both sets should match each other. It provides consistent result and is a good alternative to ratio test proposed by D. Low and in the Shift paper. Now the question one might ask is, why should I use Hamming distance for ORB descriptors? So to understand that, first quickly revisit the definition of these two distance measurement, Euclidean and Hamming. So what you see on the left, top left corner, that's a classic definition of Euclidean distance. B1 minus A1 whole square plus B2 minus A2 whole square, and then take a square root of this whole expression, and that's my Euclidean distance between two vectors. And then the definition of Hamming distance is that Hamming distance is a metric for comparing two binary data strings. While comparing two binary strings of equal length, Hamming distance is the number of bit positions in which the two bits are different. And then at the below bottom right corner below here, there are some examples of the Hamming distance. So d1 is one vector and d2 is another vector. So this is one vector, this is another vector. And if I calculate the Hamming distance between this d1 and each row of d2, this will be my Hamming distance. So again, it's just the number of bit positions in which the two bits are different. And now coming back to the reason for using Hamming distance for ORB descriptors, note that the ORB descriptors are vectors of binary values. So if applying Euclidean distance to binary vector, the squared result of a single comparison would always be 1 or 0, which is not informative when it comes to estimate the difference between the elements. So the overall Euclidean distance would be the square root of the sum of those ones and zeros. Again, not a good estimator of the difference between the vectors. That's why Hamming distance is used. Here, the distance is the number of elements that are not the same. You can calculate it by simple Boolean operations on the vectors as shown in the figure below. That is the figure at the bottom right corner. Now coming back to our code of this BF matcher. So this function create matching object has already returned me the object after applying the BF matcher function. So this is the first step of using the BF matcher function. That first you have to create this object, specifying the distance you want to use, and also whether you want to cross check at true or false. And the next step is to get the actual matches between two sets of descriptor, that is descriptor 1 and descriptor 2. And for this, I have two function, which is bfmatcher.match and bfmatcher.knmatch. The first function, that is bfmatcher.match, returns me the best match. And the second function, bfmatcher.knmatch, will return me k best matches. So it feels like that knn match gives more choices and the candidate points are more likely to contain real matching points. In other words, knn match returns n best matches in descriptor 2 for each descriptor in descriptor 1, which means instead of a list of matches, you get a list of matches. The main advantage of using knn match is that you can perform a ratio test. So if the distance from one descriptor in descriptor 1 to the two best descriptors in descriptor 2 are similar, it suggests that there are repetitive patterns in your image. For example, the tips of a picket fence in front of a grass where there will be many repetitions. Thus, such matches are not reliable and should be discarded or removed from your model. Alright, that's enough of discussion on the BF matcher. Now let's write the code. DF, let's call it Keypoints matching. And it takes feature train image as a first input parameter, feature, and the next one is feature query image, feature code, and method. Brute force equal to, so I can use my earlier defined function here, create matching object, because that's the first step. I have to get the object of the bfcv2.bf matcher, and let's pass method and cross check true 0. Cross checking. Let's set it to true. And now best matches would be equal to bf dot match and feature train image and then feature query image, and then sort the features in order of distance. The points with small distance, that is more similarity, are ordered first in the vector. Let's do that. Raw matches equal to sorted best matches let's make use of a lambda function here. Lambda that would be x dot distance. SDX. Yeah. I want to print it here. Print raw matches with brute force. Sorry. Brute force, and then print the len of raw matches. And finally return raw matches. All right. So that was using bf.match. Now, for the sake of checking out and experimentation, I will use as well bf.knnmatch to get the k best matches in my next cell. So again, for cases where we want to consider more than one candidate match, we can use KNN based matching procedure. Instead of returning the single best match for a given feature, KNN returns the k best matches. Note that the value of k has to be predefined by the user, that is by you, as we expect KNN provides a larger set of candidate features. However, we need to ensure that all these matching pairs are robust before going further. So anyway, let's implement the same function for KNN match, and that's just copy pasting this function, and then instead of match, I will have KNN match. Yeah, and remember this function is coming from CV2 BF matcher class. All right, let's name it keypoints matching. Sorry, keypoints matching KNN. KNN. And other things I think remain the same. Method cross check remains true. Okay, for KNN match, let's put the cross check to false. I'll come back to this explanation in a while. BF, otherwise raw match, best matches. Oh yeah, because in this case, no, I have to change this function a little bit for KNN match. Let's do that. It will not be best matches because KNN returns me k best matches. So let's put my raw matches here itself. Let's just name it raw matches. Raw matches. And then I have bf.knn match, feature train image, feature query image. And yeah, I have to mention the k value. So let's mention k equal to 2. That's like one of the most common value that you use for KNN match. And then delete this line. I am printing raw matches with KNN. Len of raw matches. Okay. Then I want to get the matches. So let's create the list because again KNN will return me a list of matches. So get that list MA KNN MATCH, yes, equal to, and then loop over the raw matches for M n in raw matches if m dot dis, sorry, no, sorry, distance is less than n dot distance distance into the ratio RATIO ratio. I defined ratio? I don't think so. Let's define the ratio. That will be another parameter to this function. Ratio. Sorry. Ratio then matches dot app and a m. Oh, this will be my KNN matches. And ultimately return me the KNN matches. All right, that should work. So with this, our match points are also ready. Now I have to use another function to draw these match points. So let's quickly check out the documentation. 1 second. Yeah, so this is OpenCV documentation, and now next I'm going to use this function draw key points. Sorry, draw matches. To draw the match points. So let's just quickly read through what the documentation says, that like we used cv2.draw key points, which indeed I used to draw all the key points. To draw the key points, cv2.draw matches helps us to draw the matches. It stacks two images horizontally and draw lines from first image to second image showing best matches. There is also cv2.draw matches KNN, which draws all the k best matches. If k equal to 2, it will draw two match lines for each key point. So we have to pass a mask if we want to selectively draw it. Let's see one example. All right, so that's the documentation. Let's get back to our code. First, I'm just printing what exactly in this cell I'm doing. Drawing matched features. Yeah, that's what I'm doing here, and the algorithm used here is FVATURE features to match. Remember, we have defined this at the very top of this notebook to be shift algorithm, SIFT. All right, big equal to .5g. Because I have to draw the figures, the plot here, so let's define the plt.figure fixed size. Let's put it 28. If, wow, features to match. Yeah, features to match. Sorry, a quick correction. Features to match, I just mentioned that at the top it has been defined to be shift. No, actually it has been defined to be BF, that is brute force matcher. The shift was defined to be that's a variable for features to extract. Let's quickly just check. Yeah, feature extraction algo was defined to be shift, and feature to match was defined to be BF. All right, now, yeah, if features to match go to BF. So I will be checking for both brute force match and then also for KNN best matches. So that's why I'm using this if function here. Yeah. Then maybe say yes, match is equal to key points matching. Yeah, that's the function I'm going to use. We have already defined it. And the first parameter of this is key point matching, feature train image. Yeah, feature train image and feature query image. Feature query image method equal to a feature extraction. Yeah, this will be my shift algorithm, which has been defined in the variable named feature extraction algo. Feature extraction algo. All right. Yeah, that's okay. Now mapped feature mapped feature images equal to match feature image equal to cv2 dot. That's what I'm going to use. Draw matches, DRAW. Draw matches. Yeah. And this is the parameters that draw matches take. Image 1, this is the first source of the image. Key points 1, this is key points from the first source image. Image 2 is second source image. Key points 2, this is key points from the second source image. Matches 1 to 2. This actually matches from the first image to the second one, which means that key points 1i has a corresponding point in key points 2, then within the square bracket matches I. And out image, what is out image? Out image is just its content depends on the flag's value, defining what is drawn in the output image. And for flags, there are various values been defined. I really recommend you quickly check the documentation. It will all be very clear. Actually, it's very simple. It's just you provide two sets of image, two sets of key points. As simple as this. And yeah, let's do that. So it will be all clear. Yeah, my image 1 is my train photo. And key point should be key point 1 will be my key points train image. Key points. I think this variable key points train image. We already have got all these variables calculated above in the notebook. Key points train image, and then the next one is query photo, and the key points for the query photo as well, which will be key points query image. All right. Yeah, and okay. So, and key points query image. Okay, matches. Now, 1 second. Matches. Then I have to provide the match 1 to 2 parameter, which is this variable. This variable matches. So. From beginning to 100, and the next parameter would have been output image. Its content depends on the flag's value. Okay, output image, I'm keeping it none for now. And the last one is flag. And for flags, I am going to select flags. Flags equal to, yeah, CV2. This one I got from the documentation. You can check out their official documentation. Draw CGS flags, not draw single points. Yes, this one I want to select flags, not draw single points. Okay, that is done. And then the next condition, elif if feature to match is Canon, feature match is KNN, then CGS match is equal to, then in this case I have to make use of the other function, which is keypoints matching KNN. If URI feature train img, this one will remain the same. Then also the next one, which is feature query image. Actually, I can just copy paste from here. Yep. And in this case, the mapped feature image will be mapped feature image. Let's name it KNN. cv2.dr. Oh, sorry. That's equal to draw draw MAT draw matches, and inside I will have train photo, key points, train image. I can just again just copy paste. It'll be faster. And then let's change. Do I need to change anything? Train photo, key points, train image, key points, np.random choice. Yes, the matches need to be different. So I have the first parameter as a train photo, then key points, train image, query photo, key points, query image. Next one would be the match parameter. So let's do it like this: np.random dot ch1ce choice mat matches ches 100. The next one is output image. I'm keeping it at none. Flags is again remains the same. Okay, so both condition is satisfied. Now plt.show. I'm show will be mapped feature image. Yep. Now let's run this cell. Yes, so all the key points, the draw matches function just produce these horizontal two images, and all the straight lines are drawn based on the key points, matched key points indeed. Okay, so this one was produced with my brute force algorithm. That is when the matcher is brute force. I also want to do the same for KNN. So repeat this code in my next cell. And in this case, I want to specify. Remember our original feature to match was set at BF at the very top of the notebook, but here I want to run it for KNN, and hence let's modify that feature to match equal to KNN. That's the only change I have to do, otherwise the same code should run. Yes, let's run it. Key points matching missing one record position argument ratio. Oh, right. Yes, I have to provide ratio. Yeah, let's do that. So the problem arises from the fact that I missed providing one argument to this function, key points matching KNN, and that argument is ratio. Very important argument. Look at the original function when I defined it. It takes a ratio parameter here before the method, and I missed providing here that. Now, that's what I'm going to correct now. So my ratio would be equal to 0.75. And a quick note on this ratio. So why I would need a ratio here? So to make sure, the reason is that to make sure the features returned by KNN are well comparable, the authors of the Shift paper suggested a technique called ratio test. Basically, we iterate over each of the pairs returned by KNN and perform a distance test. For each pair of features, F1, F2, if the distance between F1 and F2 is within a certain ratio, we keep it. Otherwise, we throw it away. Also, the ratio value must be chosen manually. In a sense, ratio testing does the same job as the cross-checking option from the brute force matcher. Both ensure a pair of detected features are indeed close enough to be considered similar. So that's pretty much the job of the ratio. And now I mentioned my ratio here to be 0.75. And I have to do the same for my other implementation of the same code, which is here below. Key points matching KNN. This function takes a ratio right here equal to 0.75. All right, now it should run. Yes, finally I got the draw key points function producing results for both brute force matcher, which is here, and also for KNN matcher, which is here. Oops, I think I made a small mistake. This last IM show should be image underscore KNN. Because now I'm displaying this image, this matching, which is drawn based on the KNN algorithm. All right, so the variable is different. Yep, let's just run this cell. Yes, now that shows the correct image. And I can see that some of the features between the brute force and KNN do not match. For example, notice this last line here. This matched feature between these 2 points, this was not there. This is there under the KNN, but this particular line was not there in the brute force draw. So the last line that I just noticed was somewhere here under the KNN, but it doesn't exist under the brute force image. Now, to understand the homography matrix mathematically, I found this very nice and very well written blog by Satya Malik. He's very well known in the OpenCV community indeed. So what he's saying that so homography matrix is basically a 3 by 3 matrix, but with 8 degrees of freedom. And here he gives an example, very nice and very simple example, that 2 books here. Consider the two images of a plane, and that is the top of the book shown in this figure. The red dot that you see here represent the same physical point in the 2 images. So I have the red dot here and also the red dot here, and they are in the same plane, but this book is of course translated. This image is translated because it's rotated. Now, in computer vision jargon, we call these corresponding points, that is the red dots. Figure here shows this whole image shows 4 corresponding points in 4 different colors: red, green, and orange. Can you see this orange dot here and the green dot here? And a homography is a transformation that maps the points in one image to the corresponding point in the other image. That is homography. The homography matrix will just somehow relate these corresponding points between the images. And let's see the mathematical representation. So since a homography is a 3 by 3 matrix, we can write it as below here. And let us consider the first set of corresponding points x1, y1. That is here, x1, y1 in the first image, and x2, y2 in the second image. x2, y2 is a corresponding point to x1, y1. Then the homography H maps them in the following way. So I have x1, y1, a vector equal to h. H here represent the homography matrix, that is this one, multiplied by x2, y2, this vector. And then when you expand h, you obviously get this whole form. So this is the equation. This is a representation equation. Now, the next point. So this above equation is true for all sets of corresponding points as long as they lie on the same plane in the real world. In other words, you can apply the homography to the first image, and the book in the first image will get aligned with the book in the second image. So you apply the homography matrix on this book, this first image, and then this first image will be aligned with the second image. That's the purpose here. All right, now you can this is the link, learnopencv.com/homography example using OpenCV Python C. I definitely recommend you go through this blog. It's really very simply and greatly written. All right, now let's move ahead. So the next question is how to calculate homography. And a RANSAC algorithm, or random sample consensus algorithm, is to rescue. So RANSAC is used to estimate a homography. It computes a homography and gives you a prediction for which pairs are inliers and which are outliers. So RANSAC is an iterative algorithm to fit linear models. Different from other linear regressors, RANSAC is designed to be robust to outliers. Here I will use RANSAC to estimate the homography matrix, noting homography is very sensitive to the quality of data we pass to it. Hence, need an algorithm that can filter irrelevant points from the data distribution. And RANSAC is just the best suited candidate for that job. And now, how is RANSAC used to estimate a homography given the descriptors of both images computed with shift? So here I am trying to represent the process. So in shift, we first generate key points and the feature vector for each key point. Also, if let's imagine if k is a key point in image x and k dash here on the right is a key point in image x dash, the feature vectors give a way to tell whether k and k dash are good matches. That is, for each k, we look for a good match, which is a k dash from x dash that is significantly closer to k than any other key point in x dash. And the set of good matches forms a set of possible inliers. Then we apply RANSAC. So in RANSAC, we randomly pick 4 good matches, compute a homography from these 4, and test how good this homography is by checking how many of the good matches are consistent with the homography. That is, if k and k dash are good matches, we are hoping that in most cases the homography will map k to something near k dash. Now, good matches that are consistent with the homography are called inliers for this particular homography, and those that are not are called outliers, again for this particular homography only. Then we count the number of outliers for this homography, and then we repeat these 1000 times, picking a set of 4 good matches anew each time, and in each iteration deriving a homography and counting the number of outliers associated with it. Then, as a final step, we keep the homography with the smallest number of outliers. So here again, in a nutshell, the algorithm for finding homography with RANSAC. So all these steps to be repeated n times, and n maybe 1500 or more than 1000. So here are the main 3 steps. Select a random set of feature matches, 4 pairs of key points, and with corresponding feature vector. then fit and homography, then compute inliers, apply the transformation to all the features and compute the error. And error here means distance between matching points and the transformation. Then count number of inliers. Then finally select homography with largest number of inliers. Recompute least square H estimate using all of the inliers. That's kind of in a nutshell how RANSAC works. Now that was enough of theoretical understanding of RANSAC and the algorithm behind. Now OpenCV has already implemented this a beautiful function find homography sorry, in their module for in this segment. So I'm just going to use find homography and move ahead with our project. And here is official documentation of the find homography in OpenCV. So for the Python syntax, this is the function cv2 find homography, and let's take a quick look at the parameters that it takes. So the first one is source points. So this is the coordinates of the points in the original plane. Matrix of type cv underscore 32 fc2 or vector point 2f. All right. And destination points, this is the coordinates of the points in the target plane. Matrix of type, yeah, it's the same thing. All right, so both of these are just the coordinates of my key points. And then the method parameter takes the following values: 0, a regular method using all the points, cv RANSAC, which is a RANSAC based robust method, and cv LMEDS, list median robust method. And the final one is RANSAC reprojection threshold. I will come to explain that in a I will be explaining that in a second. Let's first get to our code to build a function to invoke these find homography. So here in this function, I'm just writing a function to which will take the key points of my from my train images and also key points from my query images, both of which we have already calculated, and then give me a homography matrix between these two source key points and destination key points. Homography stitching, and this function will take key points train image and key points query image. It also will take the matches and that parameter that we talked about, reprojection threshold, REPROJ. Let's just call it /THRESH. And then first I have to I need to be converting the key points to NumPy array before passing them for calculating the homography matrix. Because we are supposed to pass two arrays as per the documentation, two arrays of coordinates to find homography function, as if I have these 2 points in image 1 and I have points in image 2. So now I'm telling it what is the homography matrix to transform points from image 1 to image 2. That's what homography matrix will do for me. So let's just convert to NumPy array1. Key points train image equal to np dot. It should be a float 32 format. Keypoint.pt. So I'm just accessing the internal elements from my key points. You already saw that we can access the key points array from these whole vector of key points with these syntax, that is keypoint.pt for keypoint in keypoint train image here. Similarly, I will be doing for query image keypoint.pd for keypoints and keypoint query. Yeah, looks good. Now, all right. Now, for find homography, I need to have an assumption of a minimum number of correspondence points that are present between the two images. Because I have image 1 and I have image 2, and now the correspondent points mean the key points which corresponds to each other. So that kind of correspondence points, what is the minimum number? That's the assumption I need to make for this. That is, the user of this code need to make. So I'm assuming here this minimum match count to be 4. So if len matches is greater than 4, only then the following code will execute. Now construct the two sets of points, which is first will be my points train from the train images, key points train images, equal to np.load 32, and yep, key points. I have to get the points from key points train images, key point train image, then m dot q dot y q id x. I'll come to this syntax in a moment for m in matches. Okay, I think it's self-explanatory enough. For m in matches, for every m in matches, I am getting this. Okay, I have a syntax mismatch here, which is why this is coming. Oops, sorry, I think I missed the for word here. For m in matches, yes, that should work. And similarly, I have to do for the query points. Sorry, no. Points np.float. This will be my query image, and this will be my train index to for m in matches. All right, and now calculate the homography between the sets of points. So I have to apply cv2 dot find homography, and this result will be a tuple. So let's hold them in a tuple. H is my homography matrix and status. And then inside find homography, pass all the parameters. So first input is my points train. Second is second set of matching key points, which are points query. Then the method, which is cv2.ransac. And finally, the reprojection threshold. All right, and return the matches age status. And so this whole code was executed for a minimum number of matches found of more than 4. If that is not the case, then that needs to be captured in a separate variable, which in my case would be else return none. All right, that should work. Let's quickly check out if it's working. So I am going to run m equal to homography staging, pass my key points. So first will be key point train images, and then key point query images, and then matches.
And let's have the reprojection threshold at 4. Sorry. All right. If M is none, print error, else just return me matches homography matrix and STSTUS equal to M. Oops. M. And just print my, just want to see the actual outcome of homography matrix. So I'm just printing it, and let's run this, both of this cell. Awesome. I got my homography matrix printed, and just looking at the structure, you can see it's a 3x3 matrix, and this last element is 1.00, and hence this is a matrix with 8 degrees of freedom. 1, 2, 3, 4, 5, 6, 7, 8. All right. Now, quickly check out. Let's understand these reprojection threshold parameter given to find homography function of CV2. So I'm going to the official documentation here. So what they say that these RANSAC reprojection threshold for the Python syntax, yes, RANSAC reprojection threshold, and this is the maximum allowed reprojection error to treat a point pair as an inlier used in the RANSAC method only. That is, if destination points minus convert points homogeneous of H into source point is more than RANSAC reprojection threshold. Remember, this parameter is just a threshold. So this condition, if this is met, that is this expression of the left hand side, if it is more than this threshold, then the point I is considered an outlier. If SRC point and destination points are measured in pixels, it usually makes sense to set this parameter somewhere in the range of 1 to 10. Okay, let me also explain it in a slightly simpler and slightly different language. So the RANSAC algorithm calculates a whole estimation of homography matrix H based on a threshold value, and that's this threshold value, RANSAC reprojection threshold. And how it is working here is as follows, that RANSAC computes the error between the observed projection DST point, DST point here. This is SRC point and this is DST point, source point and destination points, and both are key points, of course. Remember again, these are coordinates of the points in the original plane. So RANSAC computes the error between the observed projection DST point and the projection of SRC point computed with the candidate homography matrix H. Then it just does a simple threshold check, and that threshold check is done based on this value. And this value is need to be set by the user. The user can set the RANSAC reprojection threshold value to whatever value he finds that works best for the data. If you are in a pixel coordinates, you set the maximum error in pixel distance for a point to be considered an inlier. Anything with greater error is considered an outlier. And RANSAC algorithm will simply choose the homography matrix that maximizes the number of inliers based on the threshold you set. So the mask it returns, that is a RANSAC, that is the whole this function find homography. The mask that this function returns to you is a set with the greatest number of inliers, and that inliers calculation is dependent on this threshold value that you will set during your coding process. So coming back to our code, so we have already calculated the homography matrix. Here is what I printed, that it's a 3x3 matrix with 8 degrees of freedom. And now that, and this homography matrix is basically the description of how one point in image 1
matches one point in image 2. So after this homography matrix calculation, I need to warp one of the images to a common plane. So we can do that with OpenCV function called cv2.warp perspective. So basically what I'm going to do that after calculating the transformation matrix, which in this case is this value that this homography matrix, this is our transformation matrix. So after we calculated that, now I have to apply the perspective transformation to the entire input image to get the final transformed image. So something like this kind of transformation. And this is the OpenCV documentation for this function warp perspective. So the first parameter is this input array is our original image that you want to warp. The second parameter is our transformation matrix M, which has already been calculated from our function homography stitching. And the final parameter that I need to input is the is a tuple that would be used to indicate the width and height of the output image. Let's quickly go through what they're saying in the documentation. So it says applies a perspective transformation to an image. The function warp perspective transforms a source image using the specified matrix. When the flag warp inverse map is set, otherwise the transformation is first inverted with invert and then put in the formula above instead of M. The function cannot operate in place. SRC input image, destination output image that has the size and the same type as SRC. M is a transformation matrix. It's a 3x3 matrix. D size size of the tuple, and flags. Okay, that pretty much what I need to supply. Okay, let's get back to code. All right, now I am going to calculate the width and height that I want first. So this width, I can just add the widths of the individual images. And also for the height. So that basically I'm just adding the original width of the original two images. So query, let's see that what is my width. Query photo dot shab shape 1 train photo. So I'm just from the shape of the original query photo and the original train photo, I'm just taking their shape and then taking the 1th element, that is the second element from it to get the width. Train photo, yeah, dot shap shape 1 dth 2922. Okay, let's I want to keep this thing when I write more code in the same cell. Okay, 2922 is the width when adding the individual width of both the original images. Now get the height. For height, I'm just taking the maximum height between both of these original images. Height equal to max query underscore photo up dot shape 0. And also train underscore photo dot this shape 0. And now the max will take the maximum height of them. There's a train GHT. And maximum height is 819. All right. Now proceed further. So yeah. Now just plug that homography matrix that I have already calculated here into warp perspective function, and then I shall have a warped image. Then I will have warped image 1 into image 2 frame. So yeah, result cv2 dot wrp warp perspective. Yeah. SRC input image.
my input image is a train photo. The homography matrix is homography matrix, and the size, this d size will be a tuple, and that's my width and height that I just calculated. All right. Yeah. Now, just print the result. Yeah, so this is output from my warp perspective function. So the warp perspective function returns an image whose size is the same as the size of the original train image. Hence, so this whole matrix that I can see right now as an output, this is the train image. We can actually do a quick printing of this to check it out if it's really so. Let's do plt.foj big size. Let's set it to 2010 and plt.ax. And then finally plt.imshow. Sorry. Yeah. So this image that has been shown here right now, that's a train image. Let's go to the very top of the notebook to check out if it's really so. Yes, indeed. You can see this image. This was my original train photo, and that has been printed out or output. That's the same output that I'm getting for my warp perspective function, because that's what it is expected to do, and hence this result need to be, this matrix of the result need to be changed to match my query photo. So let's just all right, so what I'm going to do is result set the height and width of result equal to the query photo's height and width. Okay. Query photo, sorry, that would be my original query photo. So just query photo. Query photo dot shape 0. Similarly, 0 to query photo dot chp shape 1. So I'm just taking from the shape of query photo, I'm taking the 0th element to set the 0th element of result, and similarly from the shape of query photos, I'm taking the 1th element to set the 1th element of result. And that would be equal to my query photo. All right, now if I plot this, that should give me clear output first. That should give me the ultimate result, what I want. Awesome, that's absolutely fantastic. So this is the final output, and you can see that it has created a panorama. Let's quickly check the original two photos again, so you can understand. So this is my query photo. It ends here. Remember this tall, the famous building in Singapore? So that's where the query photo ends, at the start of the first building. And the train photo starts at this building and has all the way up to the rightmost point. So now these two has been merged and stitched, and this panorama has been created, matching each of the key points. So again, to summarize what I did, I got the original two images. Let's actually go back to the slide that I made for this to summarize the overall steps. So yeah, the original problem was that we had two separate images. One is train image and one is query image, and they had some areas common.
And the problem was that we had to stitch these two images to create a panoramic scene. And these were the 4 steps that we implemented to create them. Detect the key points and extract local invariant descriptors using shift or surf algorithm from the 2 input images, then match the descriptors between the 2 images, then use RANSAC algorithm to estimate the homography matrix using our matched feature vectors. Finally, apply a warping transformation using the homography matrix obtained from the previous step and create the final panoramic scene that we can see right here. All right.
That pretty much wraps up this video. Stay tuned. My next few videos will all be on OpenCV, image processing, and computer vision. So if you have not subscribed yet, do subscribe. And if you have liked this video, smash the like button. See you in the next video.